Good morning. Happy Friday. Good to have you here. Several weird things happening next week because Monday, of course, is Memorial Day. And I hope you all have a great Monday and stuff. Not it's totally closed. Don't come to campus. I will be here. No office hours, no lab, nothing like that. But because of that, our schedule is a little weird here in Section 01. So next week, Wednesday, it's important that you come to lecture at 9 o'clock on Wednesday to this room. And you'll turn in the QA1 lab as well as exam prep 2. And then next week, Monday, the week after, which is, let's see here, what day is it? June the 3rd, there we go. June the 3rd at 1:10 p.m. We'll take the second midterm, which we would have taken next week, but obviously not. We'll take the second midterm, and then afterwards we do have a lab. It's QA3. QA3 is a lab you'll turn in at the end of lab, so it shouldn't be too bad. There are a couple of cheesy post-lab questions, which are kind of similar to the post-lab questions from QA1. If you want to get ahead of it, you can work on them anytime. Most of the answers are in the front page like they were before. Bring your goggles, no open-toed shoes to that lab, stuff like that. The exam itself, 20 multiple choice questions, 5 short answer questions. There's 5 points of extra credit built into it. Any questions?
5 points bonus for what?
Sorry?
5 points bonus for what?
Extra credit built into the exam. So there's like 100, I think the exam is like 140 points, Brandon, so there's a total of 145 points total, but you don't have to think about it, just write it out. So. Cool. All right. Very cool. So what we'll do is we'll do some more of this exam review. I probably won't get through all of the examples today because we don't have another day on Monday. But I'll post a link to Discord. It's the complete exam 2 review. And if you want, you can go back and check that out later and see what's going on. So, but don't, whatever. All right. So without further ado, here's a question that's very typical of the stuff from chapter 16. And in this question, you need to calculate delta G using the information that's given. And you can see that there's delta H and delta S. So see if you can figure out what the value is for delta G using that information. Well done. If you've ever seen magnesium burning in air, it's very spectacular. It's very, very bright. They use it for flares and stuff when they're in the wilderness searching for things and stuff like that. But the reason I bring that up is not to show you how cool I am, but it's to show that it's a reaction that occurs very readily, all right? And so if you know that, then the sign of delta G is going to be negative because things that occur will have negative values of delta G. Things that are harder to go will have positive values. But you don't have to know that magnesium burns in air. It's no big deal. What you do need to do is do delta H minus T delta S. The one funky thing, remember delta S is usually in joules and delta H is usually in kilojoules. And so you have to convert one to the other. I would take S and turn it into kilojoules because all of your answers are in kilojoules. But if you do that, you should get answer B, negative 568.9 kilojoules per mole. This just means per reaction. Sometimes you see them, it's not critical. Sometimes you'll see just kilojoules per mole and it's implied that it's the reaction. Don't lose any sleep over that one. This is a spontaneous reaction because delta G is a negative number. And again, spontaneous means it's going to occur. If it was a positive delta G, that would be called non-spontaneous, and those won't occur. Also, delta H is a negative number. This means not only that it's exothermic, but this reaction is enthalpy favored. Enthalpy wants delta G to be negative. On the other hand, delta S here is a negative number. Positive delta S's imply entropy driven. So what this reaction says is that entropy doesn't want this reaction to go. And almost any time you go from a gas to a solid, entropy is going to be, no, I don't think so. But at this temperature, delta H is able to overpower it. So this is spontaneous, enthalpy favored, but it is not entropy favored, entropy disfavored. Any questions? Cool. Here's a reaction where, unlike the last one, which they were both negative, here we have a delta H which is positive and a delta S is positive. And so I'd like you to think about which one of those would be appropriate for this set of delta H and delta S. It's kind of the opposite of what we just saw because both values here are positive. So see if you can figure out which of those would be the best descriptor. Prof hat off. I'm embarrassed, but Allie, you'll appreciate this. I think my cats were on my computer last night. Anyway, prof hat really on this time. Sorry, that was totally inappropriate as your professional instructor. All right, sorry. Okay, so cats. Anyway, prof hat back on. So if something is product favored, all right, what will be the sign of delta G for a product favored reaction?
Negative.
Negative, that's right. So if we want something product favored, we want delta G to be a negative number. Those are the reactions that occur, all right, like magnesium making magnesium oxide. And to figure out if it's going to be negative or positive, there's two parts. And I'm just going to put these kind of in brackets. They're not like absolute value, but we'll think about it that way. And the two parts that will make that up are the delta H term and the minus T delta S term, all right? So in this problem, delta H is positive. Now, positive delta H does not make delta G negative, all right? Positive delta H would make delta G positive. So what this is saying is enthalpy doesn't want this reaction to go. This is an enthalpy disfavored reaction, all right? This is endothermic. And up until this chapter, we would say exothermic reactions are usually the ones that occur naturally. And it's true, endothermic reactions don't contribute to negative delta Gs. So if you see a positive delta H, that doesn't want the reaction to go. But now let's look at entropy. So entropy here is a positive number. And a positive delta S times the negative right there makes this whole part negative. So positive delta S, which is what we have here, times negative makes this whole part negative, and that makes delta G want to be negative. So we call positive delta S's entropy driven because entropy in this case wants delta G to be spontaneous. It wants it to be negative. It wants it to be product favored. So in this problem, we have like a fight going on, all right? Enthalpy says, I don't want this to occur, but delta S says, I want it to occur. Now, like we saw in the last problem, delta H is usually kilojoules and delta S is usually joules. So usually delta H is a lot bigger, all right, than delta S. If the temperature, though, gets big enough, then the minus T delta S part will overpower the delta H term. So if we can make the temperature high enough, and high is very relative, there's not like a definition. You can calculate it if you have the values, but at higher temperatures, this part will overpower this part, and delta G will be negative. So if you look at this thing right here, product favored at all temperatures? No, all right? Positive delta H usually will say, nope, I don't want this reaction to go, and delta H is usually bigger than delta S, all right? But on the other hand, the last one, not product favored at any temperature, no, that's not right either. Because eventually, we're going to get a temperature that's high enough so that minus T delta S becomes bigger than delta H, and then delta G will be negative. So it's not going to be A, it's not going to be D. There's going to be product favored possibilities, but we have to decide, of course, if they're high and low. And for this one, because delta S is positive, we want higher temperatures to make this whole thing spontaneous. So this reaction would be product favored at high temperatures, all right? If you have both positive delta H and positive delta S, then higher temperatures will allow delta S to overpower delta H, and that's how that works. On the last example with magnesium, we had two negatives, all right? Now in those cases, it's enthalpy driven, entropy disfavored. So those reactions would be product favored at lower temperatures, quote unquote. And again, high and low is very relative here, all right? It may be 1,000 degrees, it might be 10 degrees, it's hard to say. But you will have it product favored sometimes, not all the time, but sometimes. And of course, it won't be that. This would be negative delta S and positive delta H. This one would be negative delta H and positive delta S. Questions on that? Cool. Okay, if you have all the delta G values, you can go delta G products minus delta G reactants. But to be honest, a much more common example is one like this, where you have a delta H set of values and an S set of values. So what I'd like you to do on this problem to find delta G is find the delta H of the reaction, products minus reactants. And the same thing for entropy. I want you to find the entropy of the reaction, products minus reactants. And then when you have all that, you can go delta G equals delta H minus T delta S. Now remember that there are some non-zero stoichiometries here, non-one stoichiometries. So you want to multiply the H2O2 by 2 for both delta S and delta H, as well as the water. All right, this one you can leave alone, but make sure you throw these in. See if you can figure out what the answer is. Cool. All right, so this one is tedious, but it should be just plug and chug. And what you do for delta H, products minus reactants. So 2 times water, there's no O2 because the elements in their natural states are all 0. So you go 2 times water, this number, minus 2 times this number, the H2O2. That makes that whole part positive. You get a delta H value. Same thing for delta S. This time you do have to include the oxygen because the only time you have a 0 entropy is perfect crystals at 0 Kelvin, which is essentially never. So they're almost always positive numbers. So you go 2 times this plus this minus 2 times that. You get delta S. Delta G, equals delta H minus T delta S. Make sure you turn the joules into kilojoules. I think you all are taking care of business on this. Final answer, minus 233.5. Here's the delta H value. It's a negative value, so it's exothermic. Exothermic means this reaction is enthalpy favored. When you calculate delta S, positive delta S, so it's entropy driven. And again, note the joules, not kilojoules. So when you combine them at the end, convert one into the other. I turn joules into kilojoules just to make it make sense with the answers. This reaction is spontaneous. This reaction will be spontaneous at all temperatures. All right, you've got an enthalpy and entropy driven reaction. Can't stop this train from going. Questions? Now, here's another kind of question. We have a delta H and a delta S value listed, and we're slowly increasing the temperature. And the question is, will there be a temperature? And if there is, what is it? What temperature will it become non-spontaneous? So think about how you can solve this. Punchline, you'll let delta G equals 0, and you'll find that temperature, that threshold temperature, where you go from spontaneous to non-spontaneous. See if you can figure out what the temperature is. Yeah.
Maybe I should get the question better.
It's okay. Glad to have you here, Jake. That's what this time is for.
Student in the long way.
Yeah, that's okay too. So,
Did not pay attention to the jewels.
yeah, no, it's easy to do these kind of things. So in this problem, we have an exothermic reaction. Delta H is negative. Enthalpy driven is another term for exothermic. And that means that delta H wants this reaction to occur. But on the other hand, delta S is negative as well. And delta S, it's negative, means that entropy doesn't want this reaction to go. So like we talked about earlier, if delta S is big enough, i.e. if temperature is big enough, then delta S will dominate the value of delta G. Normally, here delta H is usually bigger because it's in kilojoules, while S is usually in joules, but you can't get to big enough temperatures where the delta S term will dominate. So what I'd like you to do on this problem then is essentially solve for temperature. And so you can let delta G just equal 0, because that's when it goes from non-spontaneous to spontaneous, or vice versa. So if you put negative T delta S on the other side, it becomes positive T delta S. And if you divide both sides by delta S, temperature equals delta H divided by delta S. And like Jacob and I were kind of talking about here, remember that delta H is usually in kilojoules, while delta S is usually in joules. So you have to convert one to the other, it doesn't matter. It comes out in Kelvin, not Celsius initially. If you got the 7,620 Kelvin, well done. And what this number says for this problem is that at this temperature, delta S dominates delta H, okay? And because delta S is negative, that means you're going to be non-spontaneous at 7,621 Kelvin, which is a huge high number, and it would probably be hard to get there, but it might be possible on an industrial scale. What I would do, of course, is do this closer to room temperature where it would be spontaneous. Another thing that helps about this kind of application, in chemistry, can Kelvin temperatures ever be negative? No, that's right. In physics, they talk about it. Physics maybe is a different story, but boy, not in chemistry, all right? So if you have a negative delta H or a negative delta S, you can get to a final temperature which is negative. And if you see that, all right, that means you either have a reaction which will never be spontaneous, or it's possible that you'll have a temperature which is spontaneous all the time. So if you calculate a negative temperature, you're going to have either never spontaneous or always spontaneous, but it won't be one of these kind of things where there's a threshold temperature. Only positive temperatures will give thresholds between not being spontaneous and spontaneous, or in this example, going from being spontaneous to not spontaneous. Questions? Cool. All right. Here's a problem. It has a KSP, but this really is not a solubility question. This is a question about finding Gibbs free energy. So see if you can use that value of KSP to find the delta G for this reaction. And this is an example where you'll use delta G equals minus RT natural log of K. See if you can figure out how that rolls. Well done. All right, delta G equals minus RT natural log of K. K can be any of the Ks we've seen this quarter. KAs, KPs, KFs, et cetera, et cetera. This is a KSP, no problem. One thing you can do with this equation is that reactant favored Ks less than 1, will correspond to positive delta Gs. So in this problem, we expect to get a positive number because our K is less than 1. Reactant favored means non-spontaneous. It's not going very far to products. Use Kelvin, use 8.3145 to make sure you get everything right. You get an answer which is in joules because of the R, so you can divide by 1,000 to get the kilojoules. Answer B is what pops in there. So minus 8.3145 times Kelvin, natural log of that. You get joules initially, turn it into kilojoules. Questions? Awesome. Okay, this is an example of balancing a redox reaction. And when you balance these reactions, you can initially show the electrons in the half reactions, but when you put them all together, you want to make sure the electrons are gone. Also notice the pH. Is this a basic pH or an acidic pH?
It's basic.
Basic. So at the end, you can have hydroxides in water, but don't have any H+. So see if you can figure out which of those would be the balanced reaction for that particular interaction of permanganate and iodide. on these kind of reactions, it's super critical that you pay attention to the pH. This is a basic pH. So at the end, you want to have hydroxide and water, no H plus and water, all right? What I do a lot of times on these is I will balance them first in acid and then neutralize in base. I'll show you how that works here in a little bit. But what I'm going to try and do here is do it in base, and I'm not always really good at this, so bear with me a little bit. Let's do this one because it's easier. First thing to do, balance the atoms. I'm going to add a 2 to it. By the way, I separated out the like parts into the half reactions. I forgot to mention that, sorry. I'm going to add a 2 right there because that makes the iodine atoms on both sides the same, all right? So that one now is balanced for mass, and eventually you want to balance for charge. And the only thing you can do to balance for charge is to add negative electrons. So this reaction right now has a -2 on the product side. This is 0, this is -2. And this side has -2, so this reaction is balanced for mass and charge. But the top one is where we're going to have to play with hydroxides and water. And this is where it gets a little weird. Hydroxide has more oxygen relative to hydrogen, like 1 to 1. And water has more hydrogen relative to oxygen, 2 to 1. So we need oxygen on this side, like 4 versus 2. So we're going to add hydroxides. But what's always weird is like if you add 2 hydroxides, then you can't add just H plus by itself. So usually if you double it, which is weird, it works out, but let's see if this is gonna happen. And I think it may be a little bit more. No, see, it's not that, 2 plus 2, 3, darn it. I was hoping this was gonna be simple. But let's see, 4, see, I really get stuck on these, man. All right, let's go up one then. 6 oxygens would then be 6, no, that's not right. 4 would be 4. See, is that right? 2? Okay, 6. There we go. All right. Hopefully, some of you are better at this than I am. I always get jammed up on these, man. So anyway, if you do too, you're in good company. Needless to say. But anyway, okay. I think this is good, but now I'm not feeling confident whatsoever. So I'm going to balance it. Manganese, both sides, check. 4 and 2, 6 oxygens. 2 and 4, 6 oxygens, check. 4 hydrogens, 4 hydrogens, all right. I always feel like I'm stumbling. I'll show you the acid way in a little bit if that's easier. Questions on that? Good. This side has -4. This side has -1. This is a more positive side, so you want to add electrons to the more negative, to the more positive side. So -3 and -1 makes the reactant side -4, just like this side is right here. At this point, one side should have electrons as reactants, the reduced part. One should have electrons as products, the oxidized part. So those are the 2 half reactions, all right, what it looks like when the electrons are showing. The final step is you want to multiply both of these in such a way that at the end, no electrons show. So you can probably see here that 2 electrons and 3 electrons have a common denominator of 6. I'm going to multiply this whole reaction by 3, and I'm going to multiply this whole reaction by 2. And this is where it gets kind of fun too, but make lots of space and stuff. 2 times 2 would be 4 waters and 2 MnO4 minus and 6 electrons. I'm now going to go here and I'm going to have 6 iodides. Now on the product side, I'm going to have 2 MnO2 and 8 hydroxides. And on this side, I'll have 3 I2s and 6 electrons. And now, if we've done everything right, the electrons are out here, which they are. Hydroxides are there, iodine's right there, and lo and behold, answer D looks right. Woohoo! So this is the way to balance it in base. Now, as you can see, I was fumbling, all right? I feel really uncomfortable doing the hydroxide water thing. So what I would have done here on my own is I would have done it first in acid, which I'm showing you right here. Now, in acid, you pretend to have H+. So then it's easy. Yeah, I needed 2 oxygens here. I'll add 4 H pluses there. No problem. Mix them together, multiply so that all the electrons go away. This right here is the reaction balanced in acid. acid, all right? But I can't leave it that way because it's in base. So if you need to take an acid and turn it into a base, for every H plus, you had an equal number of hydroxides. So I'm going to add 8 hydroxides to this part because hydroxide plus H plus makes water. But if you add it to the left, you have to add it to the right, like in math. So I'm going to add 8 hydroxides to this side as well. So this shows the hydroxides being added in. 8H plus and 8OH minus makes 8 waters, all right? So the acid is out of here. And then as you can see though, I have 4 waters on this side, so you have to keep it lowest terms. So minus 4 waters from both sides, and this is the reaction that I wrote up there. So either way you do it is fine. Again, I find the acid way easier for some reason, but you do it the way that works. And if you can do it, hydroxide and water, cool for school. Questions? This is the kind of question you might see. It says, which is the strongest reducing agent in the list? Think about what reducing agent means. Is that oxidized or reduced? And then see which of those E naught values you can use to figure that out. Okay, I'm running out of time, so I got to talk about this one. So anyway, this is real common. This is a table of redox potentials, all right? And when it says strongest, because delta G equals minus NFE, delta G's negative are the ones that are spontaneous, the ones that are going to occur. Negative delta negative delta G means you're looking for the biggest positive E value. Okay, that's up there. So most negative here means most positive there. But we have to think about what we're looking for. Reducing agent. Does that mean we're looking for something that's being reduced or something that's being oxidized?
Oxidized.
Oxidized, all right? These are all reductions, all right? So if you want an oxidation, you have to flip all of those around. So for example, cerium 3 plus being oxidized to cerium 4 plus would have an E naught value of negative 1.61. So if you go all the way down, the one that's going to be the best piece to be oxidized, aluminum. All right, it's the strongest one. Because when you flip that around, it's 1.66 volts. Don't worry, everybody has this kind of reaction. I see some of your faces and stuff. It's totally legit. Yeah, right on. So oxidation is reducing agents, flip things around. This becomes a positive number, so that would be the biggest positive number if you have an oxidation. It's easy to get these things flipped around. That's why I brought it up. All right. There's still a couple of questions on the review that I don't have time for, but if you look at the video, which I'll post to Discord, or I can send you the link, you can look at them and stuff. They're just cute stuff. Cool. Thank you for being here. Have a great weekend. I'll see you on Wednesday, not Monday. And on Wednesday, QA1 and Exam Prep 2 are 2. Have a great and a wonderful weekend.